So it's time for our second tutorial, bootstrapping. So what's the idea of bootstrapping? So any data that I get is just a sampling from reality. If I would take the same experiment, do it again, I would get a different set of outcomes. So in a way, the parameters that I estimate for my models depend on chance. But the question that I want to ask usually is not what's the property of my data. The question that I want to ask is what should I expect outside in reality to be there? And there's arguably two kinds of ways how I can answer these questions. Now I want to make a statement about the population that is out there. And that could be the population. What if I do the same experiment over? What if I do the same sampling over? What if I take data over and over again? What if I run my same causal perturbation over and again? There's two options of how these problems can be solved. The first one is classical statistics. And you will probably have heard a lot about it. And it works like this. We assume we know how the world works. So we have a model that we can write down of how the world works. And then under the assumptions of knowing what the world is, we can in a way calculate which models would be probable and which ideas would be improbable. Frequently the approach is that we say, well, if this is how the world works, this would be our so-called null hypothesis. If our null hypothesis wouldn't be true, this is how it should deviate from that null hypothesis. Now let's check if the null hypothesis becomes in a way improbable. So there's one option. It requires you to know how the world works. There's another option, which is bootstrapping, where instead of assuming that we know how the world works, we in a way assume that we know how our data analysis works, which we certainly do. And we basically take the data that we get as potential samples from the outside world. And let's step through how bootstrapping would work. So let's first be clear about what's so cool about it. For linear regression, we can do some semi-complicated math and solve everything analytically. But bootstrapping works for pretty much anything. Now, like there will be statistical issues like we might not have enough data, there might be some other problems, but importantly bootstrapping works on complex pipelines and it works with non-trivial models. Remember how in the first week we talked about interesting models that we were fitting? We can do bootstrapping with these models. It would be very unclear how we would be doing it with classical statistics. So in a way, it's a way of doing statistics that's very broad, that is very compatible with the modern ways how we do data science. So let's go back to the model that we had before. Now you can say we had a model where we have the mean squared error, which in the specific case that we looked at also was the log posterior. And what we did is we found our model, theta maximum likelihood estimation, which was very close to the true case. So this is that ideal case where we have lots of data points that are really, really good, which is what we chose, so that conceptually it would be easy. But in reality, you will often find data that looks much more like this, where you have a scattering of points as a function of x and y. And well, what should we do in that case? You can say, I can take the data points that we get, and I can put a fit into that. But how much should I trust that fit? No, like arguably, if I would ask you to do it by hand, you could be like, yeah, that could be like this, or maybe it could be like this. So there's many possibilities. Now the true model in this case that we actually generated the data from was the green model. Weird, no? Like the average of the points is clearly lower, and it also looks like the slope is lower. But well, that's because of the sampling that we get. It happened to be lower. So what we'd have in this case is we'd have that the maximum likelihood, that the minimum of the mean squared error would be at a different place to where the true value is. Now, is this red model fit a good estimate? or is it not? Should we be surprised if someone told us, well, the green one's the right one, or should we not be surprised? So what we want to do here is we want to understand how our estimated coefficient compares with the true coefficient. And so the solution is estimate the distribution of estimated coefficients along with uncertainty using the so-called Bootstrap. So how do we access uncertainty using Bootstrap? So what we do is we resampled from the observed data set with replacement. The number of samples is the same as the observed data set. So in a way, it's like traditional statistics where we might assume that we have a Gaussian distribution or something. Only we don't use a model of the world to produce the sample. We use the data that we have to produce the samples. And then we collect all estimates into a distribution and we analyze the coefficient, the confidence interval. So the idea there is I take the same data points that we have. It will always be the same data points, but some of the data points randomly we will pretend that we never saw them, and others we will assume that we saw them multiple times. Now, like here, the light blue ones, we saw these 2 times. The dark blue ones, we saw them 1 time as before. The gray ones, we never saw them before. So what we do is we say, based on the data that we have, let's make up an alternative outcome of the experiment. And it turns out that it has a lot of attractive statistical features. So in this case, our slope might be a theta of, let's say, 75 or something like that. Now, and we could do the same thing again, where we would get different points. Now these points were not sampled, these 4 points, but these points were sampled, and this point was actually sampled 3 times. So in this case, we would be getting a lower estimate of the slope. And we can do it again, giving us a 3rd estimate and again, a 4th estimate and again, and so on and so forth. And we do that same procedure where we resample the data many, many times, and every time we will get a different fit. And what you see here is the distribution of all possible fits. You see the true model, but you also see the distribution of estimates that we have. Now, in a way, we can already say, look, that estimate distribution is kind of overlapping with the true model. So it shouldn't be that surprising that the true model had its property. Our model fit here, and also our average model fit, is what we see in orange. So if we do it many times for the slope, we will get a certain distribution. The mean of that, we can call that theta estimate. That's what we have in orange here. Then you can say we can take 95% of the samples that are closest to it, which means we basically exclude the bottom 2.5% and we exclude the top 2.5%, and that gives us the 95% bootstrap interval. Now in this specific case, the true value was just slightly outside of it, and we might say, well, in this case it's a bad estimate based on the data that we have. It was unlikely that the real slope theta true was that large, which might make us suspicious if someone would say, well, the real true value is this. Not very suspicious, but somewhat suspicious. So how do we assess uncertainty by Bootstrap? We sample from the observed data set, we collect all estimates into a distribution, and we analyze the confidence intervals here. So here's again the data. We do the bootstrapping here, giving us the values here. If someone told us the true estimate was here, we can say this is a good estimate. Now the question is, like, how often, if the data is produced like this, how often do we get good estimates and how often do we get bad estimates? And here, assessing uncertainty by Bootstrap. In most real-world scenarios, we don't know the ground truth. No one tells us what reality is. But it's still beneficial to have a distribution rather than a point estimate. Bootstrap gives us that distribution. And with the distribution and uncertainty, we have more information to make a decision. And under certain circumstances, it tells us how we should be betting on where the true estimate really ends up. So now it's time for the notebook. In the following notebook, you will generate a simulated dataset from an underlying linear model. You will implement Bootstrap to get the confidence interval of the model fits, and you'll compare the true parameters with the estimated distribution to see how confident the model is and how confident it should be. And above all, have fun.